Hello everyone, welcome back to another video. Today's video we are going to be going over a situation where we are going to be having a heat exchanger with two currents going through it. This could be a fluid or a gas of some sort. There is going to be a hot current and a cold current going through this heat exchanger, and we are going to try and come up with an expression for Q, which is the heat being exchanged between the two fluids, and that is going to be in terms of U, which is going to be a combined heat coefficient, kind of just a constant that is used to represent the all of the different convections and conductions of heat that is being transferred throughout the system. It's pretty much just a simple way of modeling the complex way that the heat is going to be getting transferred within the system. And then this expression for Q that we're going to come up with is also going to be in relation to the changing temperatures and also the area of the heat diffuser through which the heat is actually being exchanged. All right. So over here we've kind of graphed out how the temperatures of the different currents is going to be changing as we move along the heat exchanger. All right. So as we move along the x-axis, we are just moving along the heat exchanger, going from position 1 to position 2. And our y-axis is just the change in temperature. So obviously, the higher you go, the hotter the temperature, and the lower, the colder the temperature is. All right. And as this hot current starts out, it is going to be losing its heat, and the heat is going to be going down as it moves along the heat exchanger. And this cold current down here is actually going to be doing the opposite and increasing temperature. All right. So to start out with, the difference in the temperatures between these two channels is going to be very high. Then heat is going to be getting transferred, and then it is slowly going to be approaching over here until it reaches this difference in temperature of T2 over here. All right. So over here we have our outlets over here, our temperature of the hot channel outlet and the temperature of the cold channel outlet. And then on the left side over here at position 1, we have the inlets, obviously with the cold stream inlet and the hot stream inlet. And our first step in creating our model for Q is to just come up with a basic equation to start out with. We know that Q is going to be represented by the heat capacity of whatever the compound is that is moving through the heat exchanger. And we're going to do a separate equation for both the hot channel and the cold channel. All right, so we will use CPH in order to represent the heat capacity up here. So Q is equal to Cp, which is the heat capacity, and then H for the hot channel. And then this is going to be multiplied by the difference between the temperature at the inlet and the outlet. All right, so this is going to be multiplied by THI minus THO. All right, and then obviously we can take a derivative of this in order to get how the heat exchange is going to be getting changed. So obviously the heat capacity is not going to be changing, so that will remain constant. The only thing that's going to be changing over here is this term right here, and this is just going to be represented by DTH, which is just going to be how the temperature is changing at that certain position. And as we can see over here, for our hot channel, that is always going to be negative, right? That is always going to be losing its heat. So this is going to be negative DTH right here. And then over here, when we represent our cold channel, it's going to be very much the same. This will become CPC over here to represent our cold channel. And then we will have TCO minus TCI because we want this term to be positive right here. And this outlet temperature is always going to be higher because it's gaining heat. So this will be TCO minus TCI. And then again, we'll take the derivative of this, and this will become a positive over here, since we know that the change in temperature is always going to be increasing because the cold channel is going to be gaining the heat. So dQ will be equal to CPC times dTC. All right, and these are going to be our equations that we use to represent how the heat is going to be changing throughout as we move along the position. And what we can do next is we can just say that the change in the temperature between the two channels at any given point is just going to be represented by the temperature of the hot channel minus the temperature of the cold channel at any given position. So we'll go ahead and write this out over here. Delta T is going to be equal to TH minus TC. We can see that here in our examples that we have right now at position 1 and position 2. We subtract the temperature of the cold channel from the temperature of the hot channel at that position, and that gives us the change in the temperature, right? What we will then do is we will just go ahead and take the derivative of this. So we will say d delta t. All right, and d delta t is pretty much just going to be the difference between how the temperature is changing in the hot channel minus how the temperature is changing in the cold channel, right? So these are pretty much just going to be some simple derivatives right here. We're just going to say this is going to be dTH minus dTC. All right, and what we can do now is we can go ahead and divide over the heat capacities over here for our heat transfer derivative equations in order to get the change of the temperature at each channel on its own, and then we can substitute those in over here for this equation. So we'll go ahead and do that now. All right, so our dTH is going to become a negative dQ over CPH, and then this dTC is going to become positive dQ over CPC. So we'll go ahead and write that out. Alright, and as you can see, we can go ahead and factor out a negative dq right here, and we can just go ahead and do that now. That'll be a pretty easy step. Alright, so our next step is going to be to come up with an expression for our change in the heat being exchanged, and that's just going to be pretty simple. We are going to say that dq is going to be equal to u, which is again representing all of the convection going on and all of the complicated heat transfer math that is going on within the actual heat exchanger itself. That is what U is representing. And then this is going to be multiplied by the change in the temperature, and then also multiplied by the differential change in the area. And this is differential change in the area just because this is the differential change in the heat being exchanged. If this was just the normal heat being exchanged, this would be the normal area, all right? So we can go ahead and substitute this in down here for dq, and that's what we'll go ahead and do now. Okay, so what we can go ahead and do is we can divide over the change in temperature, and then after we do that, we will go ahead and integrate both sides from point 1, from position 1 to position 2 as we move along the heat exchanger. So we can go ahead and do that now. We'll just go ahead and erase this and put this over delta T. Scooch the negative U over. And again, this will be integrated from position 1 to position 2. And this side will as well. All right. And over here on this side, this is just going to be a 1 over delta T with respect to the change in time. So that is just going to end up becoming a natural log. This is going to become ln delta T, and then we will have to evaluate it at position 1 and position 2. So we can go ahead and write that out. All right. And then over here, we can see that this expression, this U, is going to be a constant. That's not going to be changing as we move along the heat exchanger. And then over here, the specific heat of the streams isn't going to be changing either, so we can bring that out of the integral. And the only thing that's going to be changing over here is our area. This dA is just going to become normal A, so we'll go ahead and write that out. All right, so when we evaluate our natural log function over here, this is going to become the natural log of the change in temperature at position 2 minus the natural log of the change in temperature at position 1, which we can go ahead and write out. So this is what it looks like in its expanded form, but of course we can simplify this because these are natural logs. This is simply going to be equal to the natural log of delta T2 over delta T1. It's going to be the same thing, and it'll simplify things for us, so we'll go ahead and write that out. All right, and then over here for our specific heats, or our heat capacities, excuse me, we can go ahead and substitute in our CPH and our CPCs up here using our heat exchange equations. And we're not going to be doing the differential equations because, again, this is going to be represented using the actual heat exchange, not a differential change, but the full-on heat being exchanged. So we'll come up here and use this. So the CPH is going to be equal to Q over THI minus THO, and the same thing down here for our cold stream. But again, this is 1 over, so we can go ahead and flip that over and put that into our expression. So the Q over THI minus THO is going to become THI minus THO over Q, all right? So we'll go ahead and write that out. All right, there we go. We'll go ahead and clean up some space over here so we have some room to write this out. Almost there, got a few more steps we need to make. All right, so as you can see, we have a common denominator of Q, which we can go ahead and bring out, make this a negative UA over Q. And then the next thing we are going to want to do is we are going to want to put these terms together in terms of inlet and outlet. Right now it's in terms of hot stream and cold stream, so we'll go ahead and change those around a little bit. Go ahead and erase all this over here. We got some more room to write out. All right, and then we had a plus in between. Then brackets around all of this. All right. So, as we can see here, this can pretty much be simplified to the change in the temperature as we move along the initial inlet, which is position 1, right? THI minus TCI right here is going to be the same thing as delta T1. We already proven this using the graph. Over here, the same thing. Our TCO minus THO, we are actually going to need to multiply this by a negative 1 in order to make this THO minus TCO, right? Because we want this to be positive. So that negative will go ahead and be brought out and cancel out with our negative out here. So that's going to work out. That'll get rid of the negative for us. But again, this is just going to become our delta T2 right here. All right, this is what our expression is looking at right now. And we only have a few moves left to make. All we really have to do now is multiply the Q over and then divide by the natural log, which we will go ahead and do. Because we want to get this expression in terms of the heat exchange. That is what we are after. So Q is going to be equal to UA, and then that is going to be over multiplied by the change in temperature at position 1 minus the change in temperature at position 2, and that will be over the ratio of the natural logs, or not the ratio, excuse me, simply just the natural log of the change at temperature 2 over the change in temperature at position 1. Alright, so we did make one little mistake before we calculated out our final expression for the heat being exchanged. Obviously, we had to flip the signs over here for our outlets in order to get the the temperature at the hot channel to be subtracted from the temperature at the cold channel, which got us our delta T1 minus d delta 2. But then obviously we had this minus sign right here still, because that wouldn't cancel out over here quite yet. So we would instead need to multiply this term by -1, which would then cancel out the negative term. And then that would flip the signs over here. So this would become delta T2 minus delta T1. And that right there is going to be your final answer for what the expression for the heat being exchanged is going to be in relations for the area of the heat exchanger, the convection properties, and the actual heat transfer properties of the heat exchanger itself, and also the change in temperatures using the natural log over here. And yeah, this is your expression over here. This is the final answer. No more math for today's video. So another thing that we should look at is whether this expression could work for a counter current exchanger, which would entail that you would have one stream coming in from one end and another stream coming in from the other end of the heat exchanger, instead of this situation that we have drawn up where they are both coming in from the same side, all right? And we know we can say that this expression right here will work for either situation, and that is because this expression only takes into account how the temperatures are changing in relation to each other, right? It is only taking into account the change in the temperature, the difference in the temperature between the two streams. It is not taking a look at how the heat is changing individually. And if it did take into account how it was changing individually, we would need to come up with a different expression in the case that it was a counter current exchanger. But yeah, since this is only using the differential temperatures over here and how they relate to each other, we're not going to have to worry about that, all right? It is going to work for either case. And yeah, that is going to do it for today's video. I hope you guys enjoyed. If you did, leave a like on the video, comment down below if you have any questions, subscribe to the channel if you guys want to see more content, and make sure to have a good day.